All right, welcome to Regents Review number 32. Yuri is missing. I hope we can find Yuri. If anybody sees Yuri, please let me know. So we gotta do this one out. Gotta do this one without the Yuri guy. So porosity, permeability, and infiltration. Basically, properties of sediment. How much water can it hold? How fast can the water go through? There's like 4 vocab words that you really want to make sure you know. When we look over here, I'm going to color all these in. All right, so we'll unpause real quick here. I just poured water and it filled in all the empty spots. That's called porosity. So I'm going to take a second and color in all of A. And we're going to try to figure out which one has more porosity. Which one holds more water? All right, so it took a while. You can see I colored in all those with water. I probably should use Giants blue, but with water. Here's the crazy thing. It doesn't make sense. It's called counterintuitive. The porosity and permeability, neither one of these wins. Okay, I mean the porosity for A or B. You wouldn't think so, but as long as they're round and as long as they're sorted. So we studied a while ago, sorted versus unsorted. These are both sorted because they're all one size. As long as they're sorted in the same shape, they're going to have the exact same porosity. You wouldn't think it, but they fill up with the exact same amount of water. Now, the second thing is permeability. How fast can the water run through? And bigger particles versus smaller particles, the bigger particles are going to win. B would have a higher permeability. Okay, so they're a tie for porosity. They both have the same amount of empty space. But permeability, this one would win. And then the third thing, capillarity, sometimes it's water retention, it's called. But basically, if you drain both of these out, A is going to hold on to more water because it has more surface area. So even though they can hold the same amount of water, A is going to hold more water. So if you drained these out and say you put 50 milliliters into both of these, this one you might be able to recover 48 milliliters, and this one you might recover only 45 milliliters that comes out of the container. So the water will go through this faster. The water will get held onto more here. That's called capillarity. The opposite happens too. Water can move upwards. That's called capillary action. Water can move upwards in here a lot higher than it can in a bigger particle. So if we were going to answer some of these questions, which characteristic is most likely the same? That's going to be porosity. It's the same for both of those. Now, I'm not going to color in each of the diagrams. I should. I just don't have the patience for it. But if we look at these diagrams here, you're going to be asked some of the same questions. A, B, and C, their porosity is going to be exactly the same no matter what. So 40%, these two choices both could be options so far because it's the same number throughout. That means 40% of this is empty space, 40% of this is empty space, and you could fill up with water that much. Infiltration time, how long does it take for the water to get in? Does it make sense that the water is going to move very slow through this one? The water is going to move at a medium speed through this, and the water, it doesn't meet much resistance. So the water is going to move fast through there. So the infiltration time and rate are two different things. This is going to have a high rate, which would be a low time, because it wouldn't take long to win that race. So C, the infiltration time, is the lowest. So that makes sense for this one. If we were talking about rates, the rate for this might be like 10 centimeters per second, and this might be 5 centimeters per second, and this might be 1 centimeter per second, because this takes longer because it's a slower runner, slower infiltrator. For this question here, so you see they like to ask the porosity question a lot. So what would we see? Graph represents porosity. It's going to be exactly the same, so it would be choice D. The only way that you change porosity is if you mix in different size particles. If you start to have an unsorted sediment, then this is going to reduce the porosity because it's like puzzle pieces filling in the empty spaces. All right. So to sum up, porosity is how much empty space. So I had to use the exact same amount of blue color pencil in both of those. Permeability is how easy, how fast does the water go through an object. As particle size goes up, permeability will go up. That's the relationship there. And then capillarity, as particle size goes down, capillarity would go up. Now, can we see on the board here the perfect PBJ? If you have two pieces of bread, you want an impermeable layer. You don't want permeability. So you got to put your peanut butter on both sides of the bread to stop the permeability. So you want that's called impermeable, because you put your jam in the middle. Nobody uses grape jelly. That stuff's gross. You put your jam in the middle. You don't want that permeability to happen. So impermeable means nothing can get through. Find Uri. Hopefully you found the clue to where Uri is somewhere hidden in this video, and you can share where we can find Uri in the comments.